Welcome back to The Explainer. So glad you're here, because today we are looking at something literally mind-bending. Have you ever wondered how seemingly tiny individual decisions, like, say, approving a single new housing subdivision or opening just one local mine, can snowball into massive, permanent transformations of the entire Earth? Well, today we're diving into the parable of scale. We're going to look at the hard data behind exactly how human choices reshape our landscapes and what that ultimately means for the carrying capacity of our planet.
Here's the roadmap for today. First, digging down into modern mining. Second, spreading out with urban sprawl. Third, the Easter Island warning. And finally, wrapping it up with our global ecological footprint. Let's jump right in.
So, I want you to keep this framing question in the back of your mind as we go. How do small, totally rational choices end up restructuring the entire planet? Because, think about it. Each local action makes perfect economic or logistical sense on its own. But when you aggregate them, that's where the real permanent transformation kicks in.
Section 1. Digging down modern mining.
Okay, so when it comes to extracting the metals, minerals, and fossil fuels we need, there is an objective, fundamental trade-off. Basically, we have two main options. Surface mining, which by the way accounts for about 60% of U.S. mineral and coal production, is generally cheaper and safer for the miners. Why? Well, they aren't working down in deep, dark shafts. But the massive downside is that it requires stripping away all the soil and rock, causing huge surface disturbance. On the flip side, subsurface mining leaves the land up top mostly intact, but it requires tunneling, and that brings in some really dangerous risks, like roof collapses or sudden ground sinkage, which we call subsidence.
Let's look a bit closer at a pretty extreme variant of surface mining that happens in the Central Appalachian coalfields, mountaintop removal, or MTR. It's exactly what it sounds like. Heavy explosives are used to literally blast away up to 300 meters of a mountain summit just to get to the coal seams underneath. But all that blasted rock and soil, the spoil, has to go somewhere, right? So it gets dumped directly into the adjacent valleys as valley fill. Now, there are regulations out there to encourage restoring the land's original contour, but doing that at the sheer scale of summit removal is incredibly difficult, which means, practically speaking, the physical alteration to the landscape is pretty much permanent.
To really wrap your head around the scale of this operation, just think about the number 3,200. That is the number of kilometers of headwater streams that have been buried by mountaintop removal operations in Appalachia alone. 3,200 kilometers. We aren't just talking about a few ditches here. These are the starting veins of entire watersheds, just permanently buried under rock debris. It literally alters the region's hydrology forever.
And that brings us to the hidden, chemical consequence of all this physical earth moving: acid mine drainage, or AMD. See, when mining exposes pyritic rock, basically iron sulfide, to oxygen and water, it kicks off a chemical reaction that produces sulfuric acid. Check out that pH level of 2 to 3. To put that into perspective, the water draining from these sites is literally as acidic as lemon juice.
So what does this highly acidic drainage actually do? Well, the ecological impacts are pretty brutal. First off, the acid itself drops the water's pH to levels that are just lethal for most aquatic life. But it also acts like a solvent, pulling toxic heavy metals like arsenic, lead, and cadmium right out of the surrounding rock. It also leaves behind this bright orange-red sludge called yellow boy that completely coats stream beds, wiping out the habitat for bottom-dwelling organisms. And here's the real kicker. Because the oxygen, water, and exposed rock aren't going anywhere, this chemical reaction just keeps going. It requires continuous, super expensive alkaline treatment basically forever, even decades after a mine is abandoned.
All right, Section 2. Spreading out, urban sprawl.
Transitioning from digging down to spreading out, take a look at this huge disparity. Between 1945 and 2000, the U.S. population roughly doubled, a 2x increase. But during that exact same time frame, the amount of developed land area saw a 4x increase, jumping from about 25 million to over 100 million acres. Think about that. Our land consumption grew twice as fast as our population. This perfectly illustrates a massive long-term trend toward lower residential density, a phenomenon we commonly call urban sprawl. Now, this low-density, car-dependent expansion outward carries some very real, highly quantifiable externalities.
As cities stretch out, we see the permanent loss of prime agricultural soils. Because everything is further apart, vehicle miles traveled shoot up, which drives up greenhouse gas emissions. We end up paving over forests and wetlands, completely losing the free ecosystem services they give us, like carbon storage and flood control. Plus, all that new pavement intensifies urban heat islands. And on a socioeconomic level, it creates spatial inequity. Wealth concentrates out in expanding suburbs, while central city infrastructure gets left behind with a shrinking tax base.
So how do city planners try to fix this? They use a set of principles known as smart growth. Basically, these 4 steps are all about deliberately concentrating development. Step 1. Mixed-use zoning. This puts homes and businesses right near each other so you don't always have to drive. Step 2. Transit-oriented development, which builds high-density areas directly around public transit stops. Step 3. Drawing literal urban growth boundaries. Portland, Oregon actually did this famously back in 1979, legally stopping development past a certain line. And Step 4 is brownfield reclamation, cleaning up and building on old, contaminated industrial sites inside the city, rather than just bulldozing untouched green spaces on the edge.
Section 3. The Easter Island Warning. Let's pan out from modern cities for a second and look at a powerful historical microcivilization that acts as a really profound cautionary tale. This timeline tracks a dramatic sequence of what scientists call overshoot. Between 800 and 1200 CE, Polynesian settlers arrived on Easter Island and found a lush environment totally dominated by large palm trees. But over the centuries, the islanders extensively cleared that forest. They needed land for agriculture, wood for canoes, and logs to transport those massive, iconic stone moai figures. Fast forward to 1500 CE, and pollen records show the forest was practically gone. By the time Europeans showed up in 1722, they found a completely deforested landscape and a population that had severely plummeted from its peak.
The cascading impact here is just fascinating. The extraction of one single core resource, the forest, literally triggered a total collapse of the island's entire carrying capacity. Look at this chain reaction. Without big timber, they couldn't build ocean-going canoes. No canoes meant deep-sea fishing stopped, instantly wiping out a massive source of protein. At the same time, without tree roots holding the earth together, soil erosion went into overdrive, devastating their agricultural productivity. With way less food from both the sea and the land, archaeological evidence points to fierce competition over whatever resources were left, leading to intense intertribal conflict.
Consider this foundational truth. The island's resource base was non-replaceable on human timescales once exhausted, and social institutions failed to prevent its depletion. Now, historians still debate some of the nuances, like what was the exact role of introduced rats eating tree seeds, or the impact of later European diseases. But the core truth remains: they extracted resources faster than the island could regenerate them, causing a permanent ecological simplification. Let that weight land for a moment before we apply it to our modern world.
Section 4. Our Ecological Footprint.
All right, let's take the parable of Easter Island and scale it up to the ultimate macro level, planet Earth. Let's dive into this metric called the ecological footprint. This gives us a unified way to compare our consumption directly against the Earth's actual biological capacity. It's measured in global hectares, or GHA. Basically, it calculates exactly how much biologically productive land and sea area is required to produce all the resources a specific population consumes, and crucially, how much area is needed to absorb all the waste they generate.
The reality of our situation is right here in the undeniable math. Globally, the average person has an ecological footprint of 2.7 global hectares. But when you divide the Earth's total biologically productive area by our current population, the planet only gives us 1.6 global hectares per person. We are demanding 2.7 from a system that only regenerates 1.6. That leaves us running an ecological deficit of 1.1 global hectares per person.
And this deficit perfectly illustrates the condition of ecological overshoot. Overshoot just means we are consuming natural capital faster than the Earth can actually regenerate it. You might be wondering, how is that even possible? Well, just like on Easter Island, we are temporarily surviving by liquidating our non-renewable natural capital. We are rapidly drawing down foundational stocks like old-growth forests, ancient groundwater aquifers, and fertile soil organic matter. We aren't just living off the interest here, we are actively spending down the principal.
But check out how drastically this demand varies around the world. A resident of India has a footprint of roughly 1.2 global hectares, which is well under the Earth's per capita limit of 1.6. As we saw, the global average sits at 2.7.
But then you look at a resident of the United States who has an ecological footprint of approximately 8.1 global hectares per person. That is consuming vastly more than the global average.
Which brings us to this incredibly alarming number, 5. If everyone on Earth suddenly adopted the consumption patterns and lifestyle of an average American, it would require 5 planet Earths to supply the necessary resources and absorb the resulting waste. 5 Earths. And, well, last time I checked, we only have the one.
So I want to leave you with this provocative thought. When you think about those local mines, the sprawling suburbs, and the completely barren landscape of Easter Island, the data we've explored today makes one thing crystal clear. Our aggregate, everyday choices matter immensely. The big question is this: can our global society design institutions to prevent the depletion of our non-replaceable resources, or are we destined to repeat the history of Easter Island on a planetary scale? Thank you so much for hanging out with me for this explainer. Keep learning, keep questioning, and I will catch you next time.